Welcome to the second part of this week's lecture. So in the first part we had a look at systems of differential equations and we analyzed them quite a lot, but we didn't actually find any explicit solutions. And the goal, if we had a lot more time, would be to be able to solve a system like the predator-prey that we saw. But unfortunately in this course we're not going to be able to get that far. We will be able to solve some systems of differential equations, just not this particular one. But in order to get there, we need to look at some simpler systems, which are systems of linear equations, which is going to give us some of the techniques that we need in order to solve our systems of differential equations. But it turns out that systems of linear equations are super interesting and incredibly useful across science in their own right. So it kind of makes sense that we're going to do them anyway. Okay, so you might wonder, where do they crop up? Well, here's an example from chemistry. So suppose we want to balance the following chemical equation. And full disclosure here, I'm not a chemist. I hope I get this right. If I get it wrong, just send me an email and I'll fix things. Okay, so we want to balance this chemical equation, which says that methane plus oxygen goes to carbon dioxide and water. And what we want to do, really, if we're thinking about this in a mathematical modeling term, is we want to find values for x1, x2, x3, and x4, so that if we look at the reactant side of the equation, we have the same number of each kind of molecule as we have on the product side for each kind of molecule. So really, what we're doing is we're balancing the number of, in this particular case, carbon, hydrogen, and oxygen molecules that we have on the left with the number of carbon, hydrogen, and oxygen molecules that we have on the right, because matter has to be conserved. So we can start to write down some equations. So we have a look at the left-hand side of our equation over here, and let's analyze how many carbon atoms we have. Well, we've got a carbon atom for every molecule of methane that we have, and we have x1 of those. So we're going to have x1 carbon atoms on the left, and we want to make sure that it's equal to the number of carbon atoms that we have on the right. Now if we have a look on the right, for every molecule of carbon dioxide that we have an atom of carbon, and we have x3 number of carbon dioxide. So we've got to have that the number of carbon atoms that we have on the left, which is x1, is equal to the number that we have on the right. So it was pretty straightforward. If we have a look now at hydrogen, now we see that from our methane, every methane molecule has 4 atoms of hydrogen, and so we're going to have 4 times x1 hydrogen atoms coming from the methane. Our oxygen doesn't give us any hydrogen, so we're just going to look at the right-hand side now. We don't have any oxygen coming from our carbon dioxide, but for every molecule of water that we have, we get 2 atoms of hydrogen, so in total we'll get 2x4 hydrogen atoms on the left-hand side. And because we want them to balance up, here we go, we've got an equation there. And now finally we have a look at oxygen. Methane's not contributing any, but for every O2 atom that molecule that we have 2 atoms of oxygen. So we've got 2x2 on the left. And now if we have a look on the right, our carbon dioxide, every molecule is giving us 2 oxygens, so we're going to have 2 times x3 because we have x3 carbon dioxides, but we're also getting oxygen from our water over here. We're getting 1 oxygen atom for every water molecule, so in total we have x4. Okay, and so what you see we've got here is 3 equations in 4 unknowns that we would have to solve simultaneously in order to work out how to make a balanced reaction where we didn't have anything left over or not enough of something. Putting this in slightly more formal language, we end up with 3 equations that we need to solve simultaneously. Now, you've probably solved similar equation systems very often. You'll have your own method of doing this. For example, you might do something like you'll solve this one for x1 in terms of x3, and then you plug it into here, and then you'll plug it here, whatever your method. And there are many, many different ways of doing this. But what we're going to do in this lecture is develop a routine for solving systems of linear, well, we're going to call them linear in a moment, but for the moment, we're going to solve systems of equations like this in a very routine way. One of the reasons to do this is because it's created a way that computers can be programmed to solve these equations for us, which is great. It also means you don't have to really think about it. So I don't know about you, but whenever I'm trying to figure out who I should substitute into what in something like this, I can never get it straight. But if you have a routine that works every time, that's kind of useful. So that's what we're going to develop. Along the way, it's going to make us talk about matrices, which is also going to be useful. Okay, so let's just kind of formalize this a little bit. So I just mentioned linear equations. What is a linear equation? Well, a linear equation is an equation in some number of variables. So here we've got n variables. And it's an equation that you can write in the form some constant times x1 plus some constant times x2 plus blah, 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 all the way up to some constant times xn. And maybe you have plus some constant b. So what I should have also written here is that the ai and b are real numbers for our purposes. Okay, so we've got n variables and we have n plus 1 constants. So you might be thinking, well, okay, why is this linear? Well, it comes from when we have n is equal to 2. So if we have n is equal to 2, we'd have something like, let's take an example, 2x1 plus x2 plus 3 is equal to 0. And that might not look super helpful, but we can rewrite this. Firstly, I'm going to change my variables, so I'm going to call this 2x1 plus y is equal to minus 3, and do a little bit more reorganizing. Y is equal to minus 2x minus 3. And so suddenly you'll see that when we have a linear equation in 2 variables, we get a straight line, i.e. a function which is linear. So here we have our function that does something like this, minus 3, and we're going to have something, I'm going to get the slope a bit wrong, but there we go, there's our straight line. So this is why we call functions like this linear, even when we've got more variables, so we can't draw it as a straight line. But if you have, so if we've got n is equal to 2, we've got a straight line. If you've got n is equal to 3, then we have a plane, which is kind of the 3-dimensional version of a straight line. And you can go into 4 dimensions, you have a hyperplane, things like that. So they carry on having the same behavior as you go into more and more dimensions. Okay, so that's a linear equation. And surprise, surprise, a system of linear equations is just a collection of linear equations where each equation uses a common set of variables. So we've already just seen from our equations that we had back there, here we have a system of linear equations. So notice that each variable, and I should have said this when we saw it back here, but we can do this over here, each variable only appears as itself or a multiple of itself. So we don't have anything like x1 squared, we don't have any cross terms, so we don't have any terms like x1, x3, so these are things that are not allowed. We just have each variable just appearing by itself or multiplied by some constant. And to make a system, we have to be using the same variables in each equation. They don't all have to appear. So you'll see that in our first equation, we've got x1 and x3, but we don't have x2 and x4. Down here in equation 3, we don't have x1. That's fine, but we must have some of the same in all of them. And nobody must have any variables that nobody else has. Kind of. We'll see what I mean about that in a moment. Okay, so we've got linear equations and systems of them. So as we've said, there are many, many ways we can solve systems of equations, and we've done this a lot. Let's take a pretty standard, simple 2 equations, 2 unknowns, x plus 2y is equals to 2, 2x plus 2y equals 0. And you could go ahead and solve that. And I'm pretty sure if we compared how everybody in the class solves it, we'd find a bunch of different ways. But ultimately what you're doing is you're ending up with a new equivalence system which allows us to read off the solution easily. What do I mean? Well, you will end up with a step that says x is equal to minus 2 and y is equal to 2, hopefully, if you didn't make a mistake. And although we don't think of it like this, these are 2 linear equations. This really says 1x plus 0y is equal to minus 2, and the second equation says 0x plus 1y is equal to 2. So what we've really just done is we've transformed our original system, where we couldn't read off the solution very simply, into a system where we can read off the solution simply. And it's having an idea of this is the transformation that we want to make that leads us to this routine, which is going to be called Gaussian elimination. So let's think about how we can go about transforming our system of equations from things that we can't read off the solution to things that we can. What are the things that we're allowed to do? Well, we're allowed to multiply any equation by a non-zero constant. If we go back to our example over here, it would be perfectly fine for me to transform our first equation into, for example, minus 3x minus 6y is equal to minus 6. That is the same equation, essentially. It's just been multiplied through by minus 3. It hasn't changed the solutions at all. So that's a legitimate thing to do. We can also interchange any 2 equations, right? It doesn't matter which way around I write these 2 equations. I can write them like this, or I could say I want to solve 2x plus 2y equals 0 and x plus 2y is equal to 2, and I'm still going to get the same answer. It really doesn't matter which way I write them. And then finally, and this is the one that might sound a little strange, we can add a multiple of one equation to another and replace one of the original equations with this new equation. What do I mean? Well, I could, for example, I could have x plus 2y is equal to 2, and then I could add this multiple to my second equation, so I'd get minus x minus 4y is equal to minus 4, and I still won't actually have changed the solution set. Now you might want to convince yourself of this, but if you think about it, what I'm doing when I add this equation over here, in some sense I am just adding a constant to each side of the equation. Because remember, this is an equation. Whatever this is equal to minus 6. So I'm really just adding the same thing to both sides. It just happens that there are some variables in, but it's okay because I have that I'm adding them according to an equation. So I'm adding the same thing to the left and right hand sides. Okay, so if you're doubting me, go ahead and solve this new system, which I got from adding this row and replacing them over here, and you should find the same answers. Okay, so we're going to use these 3 techniques for transforming our system to get us from our system where we can't read off stuff to a system where we can read off stuff. Let me do an example. Okay, so I've got x plus 2y is equal to 2 and 2x plus 2y is equal to 0. And always keep in mind I want to end up with something that looks like x is equal to something and y is equal to something. that's the transformation that I want. So just because it seems easy at this point, I would like to do something that enables me to keep this x over here. So I want to keep this, but I would like to not have that there, not have that 2y. I'd like to have a 0 there. So if I think about the things that I can do, well, swapping, so let's go back and check. The things I can do are multiplying, swapping, and replacing. Well, I could multiply through, but the only thing I could multiply through in order to get rid of this 2y would be 0, in which case my x would also be multiplied by 0, and I'd lose that whole equation. So that's not going to work. Swapping my equations is not going to work. So the only thing that I can really do is add some multiple of equation 2 to equation 1 and hopefully pick my multiple carefully enough that it's going to make that 2y disappear. I'm going to call this equation 1 and this equation 2. Well, if I subtract equation 2 from equation 1, then I'm going to keep my x terms, but I'm going to get a 2y minus 2y, and that will get rid of my y term. So that's what I'm going to do. I'm going to subtract, and I'm going to replace row 1 with row 1 minus row 2. Okay, and I'm going to need some more paper here, so let's just add another page. Okay, so now I'm going to have my x minus 2x, so I've just done this bit of subtraction here, and now I'm going to say 2y minus 2y, so that's 2y minus 2y, and that's going to be equal to 2 minus 0, which is 2. So what does that leave me with? If I finish this up, I will have two new equations. So I'm just going to keep this as kind of working. So what I end up with now is a new equation 1, which looks like a minus x plus naught y is equal to 2, and I haven't done anything to equation 2. Okay, so all I did to go from this step to this step was I replaced equation 1 with 1 minus 2. Alrighty. So this is looking quite good, because if I multiply through by minus 1 here, then I know that my solution is going to be x is equal to minus 2. So let's just do that. And I haven't done anything to equation 2. So we've already solved for one of our variables. We know that x is equal to minus 2, but now we need to solve for our y variable. So in our second equation over here, what we want is to turn this into 0, and we want this to really become 1. That's the goal of what we want. Well, what can we do? We can't multiply through by anything, because again, if we multiplied through by 0, we'd lose the equation, so that doesn't work. Swapping equations doesn't work, so we're going to do the replacement thing. And we want to replace by adding some multiple of row 1 to get rid of this 2x. And the way to do that is to add minus 2 times row 1. So I'm going to replace 2 with 2 minus 2 times 1. All right, what do we get if we do that? Well, our first one doesn't change. Our second one becomes 2x minus 2x, so that's a 0x, plus, and now we've got a 2y minus 2 times 0y, which is 2y, and we've got a naught minus 2 times 2, so that's going to give us plus 4, because it's a minus 2 times minus. And so finally we're almost there. Remember, we want this to be a 1, so let's just divide through by 2. We're going to divide 2 by 2, and we finally end up with an equation 1, which says x plus naught y is equal to minus 2, and naught x plus y is equal to 2. And we've solved it. Now, this might not be the way that you usually do this, but hopefully if you did it a different way, you'll see that you get the same answer. And we're going to use these steps that we've been doing to create our routine solution method. Now, this certainly works, but it gets a little cumbersome, writing out equations again and again and again. And you'll notice that the way that I've written this out, I haven't been changing where my x's and y's are. So I always know that, for example, whatever is over here is the coefficient of x, whatever's over here is a coefficient of y, whatever's here is a coefficient of x, whatever is here is a coefficient of y. So one thing that I can do is simplify by just looking at the coefficients. I don't need to keep writing out all the x's and y's. So long as I keep everything in the right order, I can save a lot of time. So this is the first step towards Gauss reduction, which is to rewrite our system of equations in what's called augmented matrix form. So I'm going to write this over here. It's called augmented matrix form. So in order to do that, I just look at the coefficients. So I've got a 2, I do not have a 2, I have a 1, I have a 1 and a 2 and a 2 and a 2. And if this was an ordinary matrix, we'd just stop there. But we call it an augmented matrix because we're going to put a straight line like so, which symbolizes the equals sign here. And then on the other side of that, we put what is on the other side of our equals. Okay, so our equals becomes the straight line over here. So that's already making things simpler. So if I was to write out what our first bit of working was, we would transform this matrix into minus 1, 0, 2, 2, and a 2 and a 0. And then our next bit of working, which would say, we would say minus 1 times row 1. So we're going to refer to this as row 1 and this is row 2. Then we'd get 1, 0, 2, 2, and a minus 2 and a 0. And then our next bit of working would say we're going to replace row 2 with row 2 minus 2, row 1. So I'm going to write that as row 2 minus 2, row 1. And that gives us, reading off here, I've got a 1, 0, 0, 2, and a minus 2 and a 4. And then the final thing that we did was we divided row 2 by 2. So we ended up with 1, 0, 0, 1, and minus 2 and 2. So we are going to be using augmented matrix form for the rest of this lecture. So it might look a little weird initially if you haven't seen it before, but it does speed things up quite considerably. And notice that we can, now that we've got our matrix in this form over here, we can see, so this column here tells us about our x values, and this column here tells us about our y values. So we can read off and say, oh, x is equal to minus 2 and y is equal to 2, and we're done. All right, so let's have a look at another example. So we're going to do 3 equations and 3 unknowns, which is the most I would ever ask. I will generally try and stick with 2 equations and 2 unknowns, but occasionally there will be 3x3s. Okay, so we have these 3 equations, and the first thing that we want to do is construct the augmented matrix. So we just look at the coefficients, and we end up with 1, 1, minus 1, 1, minus 2, 3, 2, 3, 1. So those are coefficients on the left-hand side, and then on the other side of the equals, we have 4, minus 6, 7. And it's worth keeping in mind that we want to do a bunch of stuff and end up with something that looks hopefully like this. So we want to be able to read off and say, okay, well, x is equal to whatever this thing is, y is equal to whatever this thing is, and z is equal to whatever this thing is. So that's kind of where we want to head. And that would be the easiest solution. And keeping that in mind, we start to do the transformations in order to get there. So the first thing is we always, and this is going to be part of our routine when we write it down officially, the first thing is to make sure that our top left hand entry is a 1. So if it wasn't a 1, we'd do something to transform it, but hooray, it is, so we're good. The next thing that we want to do, if we have a look at our solutions here, is we want to make sure that there are no other x entries in the lower equations. So we want to make sure that we have zeros below this top left one. So what that means over here is we want to transform both of these into zeros. How can we do the transformations? Well, we have our 3 different things we can do. We can multiply through by some constant, but if we multiply through by 0, then we turn this whole row and equivalently this whole equation into zeros, so we can't do that. We can swap rows, but that's not really going to help. So swapping rows is the same as swapping equations. So the only other thing we can do is we can add a multiple of one row to another. So if we have a look, let's focus on this row over here. We want to turn this 1 into a 0. Which other row could we add or subtract in order to get a 0 there? Well, if we subtract off the first row, then we'll get a 0 there. So let's do that. So I'm going to make a note of what it is that I'm doing. I'm going to take row 2, because that's this one that I'm thinking about here, and I'm going to transform it into row 2 minus row 1. So I'm actually going to do, okay, so we're not doing anything to row 1, and we're not going to do anything to row 3, but we are transforming row 2 is going to be 1 minus 1, which is 0, minus 2 minus 1, which is minus 3, and 3 minus minus 1, so that's 3 plus 1, which is 4. And then on the other side, we've got a minus 6, minus 4, so that's minus 10. Okay. Now the next thing that we want to do is we want to get this 2, or equivalently this 2, to be a 0. And we don't really have a lot of choice again. We're just going to have to subtract off twice the first row. So let's go ahead and do that. So row 3 is going to become row 3 minus twice row 1. 1, 1, minus 1. We're not changing anything there. We're not changing anything in our second row, so let's just write that down. And now we've got 2 minus 2, which is 0. 3 minus 2, which is 1. And 1 minus minus 2, so 1 plus 2, which is 3. And now we've got a 7 minus 8, which is a minus 1. All right, so far so good. Possibly seeming a bit strange, but we will get there. So we've sorted out if we think about what we're trying to achieve, we've sorted out this first column. So next we're going to sort out our second column. And again, we're going to start by getting a 1 in the appropriate place. So in our second column, we want to have that this minus 3 is in fact a 1, because that will give us this bit to row. So here we can divide through by, for example, minus 3, because it's not going to lose us an equation, whereas multiplying through by 0 would. So let's just do that quickly. So here I'm going to replace row 2 by minus 1/3 row 2. Not changing the first row. Not changing the second row, the third row, and dividing through by minus 1/3. So here I've got 1 minus 4/3 and 10/3. All right, and now following the same principle, we're going to want to have a 0 below the one that we just achieved. So I want to turn this one into a 0, and conveniently I've just created a situation where I can say this row, row 3 minus row 2, will give me the 0 where I want it. All right, so we need to do whatever we can to get this entry to be equal to 0, and it's pretty straightforward. We can just subtract off row 2 from row 3. So we've got row 3 goes to row 3 minus row 2. Not changing anything in row 1, not changing anything in row 2. And row 2 we get 0 minus 0, which is 0. 1 minus 1, which is 0. 3 minus minus 4/3, which is 3 plus 4/3, which is 13/3, and minus 1 minus 10/3, which gives us minus 13/3. Okay, so keep in mind what it is that we're trying to do. We're trying to make sure that we have zeros in our lower triangular area and a 1 here. So if we multiply through our third row by 3/13, we're going to get our 1 there, which we want. So let's do that. So we've got row 3 becomes 3/13 times row 3. Not changing anything in rows 1 and 2. Now we just multiply everything through by 3/13, so 0 is still 0, 0 is still 0. This becomes a 1, and that becomes a minus 1. Okay, so things are looking pretty good. And we can in fact read off our first solution, which tells us that z is equal to minus 1. But we'd still like to do a bit of work and turn these 3 entries into zeros so that we can read off what our x and y values are equal to. So once we've got things in what is called upper triangular form, like this, it becomes a lot easier to clear these entries above the diagonal, because we can just subtract off the appropriate row. So we're going to start off with this entry over here, and I'm going to just add 4/3 of row 3 to row 2, which will take care of that one. So our row 2 is going to become row 2 plus 4/3 row 3. So let's just write down the things we're not changing, which is row 1 and row 3. Now row 2, we say 0 plus 4/3 of 0 is still 0, 1 plus 0 is 1, and now we've got minus 4/3 plus 4/3, which is 0, and we've got 10/3, let's just make a little note here, 10/3 plus minus 1 times 4/3, so plus minus 4/3, which is 6/3, which is just 2. Okay, you can rub out our working there. And now we would just want to get rid of these two. Here you can do this in whichever order floats your boat. I'm going to start with this one over here, so I'm just going to add row 3 to row 1 to get rid of that. So I've got row 1 becomes row 1 plus row 3. Write down the things that I'm not changing. Now I've got 1 plus 0, which is 1, 1 plus 0, which is 1, minus 1 plus 1, which is 0, and 4 plus minus 1, which is 3. So we're almost there. Final thing to deal with is this one over here, and this we can just add minus row 2, and that will give us what we want. So we've got row 1 goes to row 1 minus row 2. Again, write down what you don't want to change first. And now we've got 1 minus 0, which is 1, 1 minus 1, which is 0, 0 minus 0, which is 0, and 3 minus 2, which is 1. And so finally, we can read off our solution, which is that, so this, remember, is our x column, this is our y column, and this is our z column. And this row over here is really the equation which says x plus 0y plus 0z is equal to 1. So that gives us the solution x is equal to 1. This row over here really says no x's plus 1y plus no z's is equal to 2. So that gives us the solution y is equal to 2. And finally, we have this line here, which says that z is equal to minus 1. So this might seem like quite a strange technique if you haven't seen it before, but it actually turns out, particularly for things like 3 by 3, it's a lot quicker than trying to figure out who to substitute in and substituting in multiple ways. Particularly because there is a formalized way of working through the process. You don't have to guess who you should solve for or anything like that. So just to remind ourselves, what is it? Our goal is to take some matrix. So this is really an augmented matrix. So that's something which has entries. We'll just do this as 3 by 3, but there's a whole bunch of entries like that. Our goal is to take it to something that looks like this, firstly. And then hopefully, if we can, and we'll see cases where we can't, but hopefully if we can, what we want to end up with is something that looks like this. Because then we can read off x is equal to blah, y is equal to blah blah blah, and z is equal to whatever that is equal to. So the trick that we use to always convert into this format goes like this. So we have our 3 operations, so we haven't really looked at swapping rows, but we've certainly used multiplying a row, and we've seen adding or subtracting a multiple of a row to another row. So using whichever operation is necessary, the first thing that you do is you turn the top left entry into a 1. And once you've done that, everything else in that column becomes a 0. So if you look, that's what we did up here. The first thing we did was we turned this into a 1. Well, we didn't actually have to do anything because it was already a 1. And then the next steps that we did turned everything below it into a 0. Then you move on to the second column. And the second column, second row, becomes a 1, whatever you have to do, and everything below that you turn into zeros. And then you move on to the third column, third row, turn that into a 1, and if you had more rows, then everything below that would become a 0, and you'd keep going until you basically have a pattern that has 1, 1, 1, 1 all down the diagonal. Everything here is zeros, and you might have other stuff up here, and you have stuff on the other side. So the key thing is getting these ones here if you can. We will see situations where you can't, but this is the goal. And then once you've got to this form, which we call a row echelon matrix, then you deal with things above the diagonal and you clear those. The best way to get a handle on Gauss reduction is to practice. We're going to do 3 more little solutions here, just 2 by 2s, because what I want to show you now is the different types of solutions. So I've mentioned that there are cases where we can't find the diagonal that we want, and this is going to show us sort of what they look like. Okay, so here's our system, and it's 2 by 2, which is great, much more straightforward. So let's write down our augmented matrix. So that's going to be a 1, 1, 1, 2, and a 2 and a 0. The first thing we want to do is make sure that the top left is a 1. Well, it's already a 1, so that's great. We don't have to do anything about that. So the next thing that we need to do is anything below that 1 needs to be a 0. So we need to turn that 1 into a 0. And to do that, we can't multiply by 0, so we just subtract off an appropriate amount of the row above. So here I'm going to say row 2 becomes row 2 minus row 1. Okay, so we've got 1, 1, 2, because I'm not changing row 1. And I've got 1 minus 1, which is 0, 2 minus 1, which is 1, and 0 minus 2, which is minus 2. Okay, good stuff. And now let's think about what we need. So we've got our 1 in the top left, and we've got zeros below it. So the rule says now move on to your second column, second row, and turn that into a 1. But that's already a 1, so we don't have to do anything. And if we had more entries down here, we'd turn those into zeros, but we don't. So the only thing that we have left to do, really, is to convert this one over here into a 0. And we can do that by subtracting row 2 from row 1. So we're going to have row 1 becomes row 1 minus row 2. So I'm going to write down my row 2 because I'm not changing that. And I've got 1 minus 0, which is 1, 1 minus 1, which is 0, and 2 minus minus 2, which is 2 plus 2, so that's 4. And now I've got my solution. And my solution is that x is equal to 4 and y is equal to minus 2. And you might say, well, that's nice. Who cares? But what is kind of useful is to have a look at what this means in terms of the geometry of the system. So let's just take a moment, and we're going to sketch these 2 straight lines. So I'm just going to write them in slightly easier form. So this is y is equal to minus x plus 2, and this is in the form y is equal to minus x over 2. All right, so let's sketch those 2. So minus x plus 2, so that's going to be, let's put a 1 and a 2, 1 and a 2. So here's our graph of y is equal to minus x plus 2. And if we sketch the graph y is equal to minus a half x, then we've got, I'm going to need probably a little bit more space. So our graph is going to go through here, and when x is equal to 1, y is equal to minus a half. It's going to be something like this. So we're going to come through something like so. Whoops, and I've just got my label in the wrong place for this graph. So So let's label this graph up here. We've got y is equal to minus x plus 2. And down here I've got the graph y is equal to minus x over 2. And if I'd drawn this perfectly correctly, the thing that you'd notice is that this point over here, where they cross, is the point 4, minus 2. Because remember, when we're solving two equations like this, we're saying these two graphs, for what values in of x and y are these two graphs the same? So we're finding the point of intersection. So in this particular case, we can see, because we're using two variables, two unknowns, this solution corresponds to the intersection of these two graphs. So that's kind of cool. But it's also going to give us insight into more equations and more unknowns and the kinds of solutions that we get when we look at the next two types of solutions. Okay, so here's a system that looks very similar. So we've got x plus 2y equals 2 and x plus 2y equals 3. Let's go ahead, form our augmented matrix. And begin our process. We've already got a 1 in the top left, so we want to turn this 1 into a 0. So I'm going to say row 2 becomes row 2 minus row 1. Not changing row 2. Well, we've got a 1 minus 1, which is a 0, a 2 minus 2, which is 0, and a 3 minus 2, which is 1. And at this point, you look at it and go, but what does that mean? Because ideally, we would want a 1 here, but we don't have it. Always come back to thinking, what are the equations that this is saying? Well, this has become a set of equations that says x plus 2y is equal to 2, which is fine, and 0x plus 0y is equal to 1, which is kind of crazy. We can't have this because no matter what x is and no matter what y is, this side is always equal to 0, in which case it's never equal to 1. So what this is telling us is that for this pair of equations, there's no solution. So this is one of the key things when you are doing your Gauss reduction. If you have a row that looks like this, which is all zeros to the left of our equals line and non-zero to the right of the equal line, this together means no solution. So you might be wondering, okay, if our previous example was two straight lines and we found the intersection, what's happening over here? Well, let's sketch our solution again. So here we've got, this is the line y is equal to minus x over 2 plus 1. And this is the line y is equal to minus x over 2 plus 3 over 2. And hopefully at this point you see what's happened. We've got our two lines here. So here's my line minus x over 2 plus 1 does something like this. And my line y minus x over 2 plus 3 over 2, that's parallel to this line, but slightly higher up. So this one is the line y is equal to minus x over 2 plus 3 over 2. And so what our solution here, our no solution is saying, is that our two lines are parallel. So there are no values of x and y where these two lines intersect. So these are parallel. So you have no solution. All right, so we've got one more situation that can happen. Here's another similar looking set of equations. So we've got 1, 2, 2, and 2, 4, 4. Let's do our Gauss reduction thing. We've already got our top left is a 1, so we need to deal with this 2 here, turn that into a 0. So we're going to say row 2 is equal to row 2 minus 2 row 1. What happens? Well, we're not changing row 1, so now we've got 2 minus 2, which is 0, 4 minus 2 times 2, which is 4, so that's a 0. Oh, so now we've got something that looks a little bit like the previous case, but there's a crucial difference here. And the crucial difference is that we've got a 0 here. So thinking about the equations that this augmented matrix represents, this represents x plus 2y is equal to 2, and this equation says 0x plus 0y is equal to 0. Now in our previous situation, we didn't have a 0 here. We had some number and it was never true. But now we have the opposite situation, because this is always true. No matter what values of x and y you put in here, you're always going to have this equation be true. So this is always true. So what this is really saying is we can't find a unique solution. So whatever values of x and y we put in that make this true will automatically work here. So our solution here is, x plus 2y is equal to 2. Now you don't need to worry too much about writing that, but what we do want to think about is, what is the geometric interpretation? Well, and this is going to be obvious once we do this, I'm going to write this in my usual form. So this is y is equal to minus x over 2 plus 1. And notice, when I try and write this like so, if I divide through by 2, I've got x plus 2y is equal to 2. It's the same equation. So although we mightn't have noticed it, in fact, we've got two equations, but they're the same equations. So the second one is not giving us any information. What have we done? Well, we've really got our situation where here is our y is equal to minus x over 2 plus 1. And we've just gone and drawn the same graph on top of it. And so what we have is infinitely many solutions, because every point on that line is a solution. And this turns out these three cases are the only possible types of solutions, no matter how many variables and unknowns you have. However many equations and unknowns you have. There are only three possible things that could happen. You can have a unique solution, which in the two-dimensional case corresponds to two graphs that intersect at a single point. Or you can have infinitely many solutions, which we've just seen now. It corresponds to our two lines being overlapping and having infinitely many solutions. Or you can have a situation where you have no solutions. So that corresponds to where our two lines are parallel. So I've just summarized this over here. In the online quiz, you'll get to see some examples in 3 dimensions and probably in the tutorial as well. But you'll see that we always have the same situation. There are 3 things that can happen: a unique solution, infinitely many, or no solution. So the key thing here is learning how to recognize each of these from your final row echelon matrix. So the final thing you've got. So let me draw a sketch here. So our unique solution, you're always going to have as many equations as unknowns, and it will look something like this. So I'm just doing in 3, and you will get a solution. It looks very neat like this. You've got 1s on the diagonal, 0s above, 0s below, and anything here. You can have 0s there, that's not a problem. Infinitely many solutions, you'll probably be able to get a couple of 1s, but you're going to have a row of 0s and you may or may not be able to do stuff. So the key thing for infinitely many solutions is that you have this row of zeros, because that essentially says that one of your equations is not helping, it's not constraining the system anymore, it's kind of a useless equation. It's actually just a multiple of the other equations. So you don't, in some sense, have enough equations to solve uniquely. And our no solution looks vaguely like our infinitely many, but is very different. So we have a similar situation. You'll find some ones and you'll have zeros, but then you will have something, let's call it m. You'll have other stuff up here. M is not equal to 0. So you'll have some non-zero thing. And that's how you spot. And this over here is telling us that you have a situation where you're trying to have 0 times x plus 0 times y plus 0 times z is equal to something that's non-zero, which you can't have. So there's no solution. Okay, so in being able to identify, once you've done your Gauss reduction, which type of solution you have is important. Beyond that, reading off your solution, in this case, you need to be able to do. Not so important for the infinitely many, although I'll show you how to do it. And obviously, if there's no solution, you can't read off the solution. All right. So let's go back to our very first system where we were trying to balance our chemical equation and just have a look at how Gaussian elimination helps us here. So the first thing that you should have a look at is you would say, well, I have 4 variables, but I only have 3 equations. So there's no way I'm going to be able to solve for a unique solution. So we have 4 variables and 3 equations. So we must have infinitely many solutions. Because really, in order to get a unique solution, we need to have another equation. Well, we can always add in another equation. That's this 0x1 plus 0x2 plus 0x3 plus 0x4 is equal to 0. But to see why this is useful and why you would want to use this in chemical reactions, let's do a little bit of work. So I'm going to write out the augmented matrix. So we've got a 1 and a 0 and a -1 and a 0. And now I've got a 4 and a 0 and a 0 and a -2 and a 0. And I've got a 2, whoops, no I don't. I don't have any x1s in that equation. I have a 2, a -2, a -1 and a 0. And then I have my imaginary equation for 4th equation, which we can put in, which is all zeros here, if you like. Okay, how is this helpful? Well, the first thing I'm going to do, so you might look at this and go, well, we have infinitely many solutions, moving on. But infinitely many solutions doesn't mean that you can't tell things. So let's work through a little bit more and see what it is that we can tell. So I've already got a 1 here. So I'm going to concentrate on getting a 4 here. So I'm going to subtract off 4 row 1 from row 2. So I'm writing down the things I'm not changing. So that's going to be a 4 minus 4, which is 0, 0 minus 0, which is 0, a 0 minus -4, so that's going to give me a 4, and a -2 minus 0, which is -2, and that's just a 0. Okay. What next? Well, we'd like to have, so notice we've sorted out our first column. Our next column, we'd like to have a 1 here. Well, one thing we could do is we could switch row 2 and row 3, and that'll give us a 2, and then we can divide through by 2, and that will give us a 1 there. So we're going to switch row 2 and row 3. Okay, and now I'm just going to divide through by 2 to sort out this into a 1, and I'm going to divide in the same step. I'm going to divide through by 4 to get my row 3 to have a 1 there. So I'm going to say row 2 is 1/2 row 2, and row 3 becomes 1/4 row 3. And what else can I do? Well, I'm not going to be able to get rid of these are halves, but maybe I could get rid of this over here, this -1. So I'm going to say row 2 plus row 3. Now I know that I'm going through this fairly quickly because I'm not generally going to expect you to do this. But I do want to do this just once so that you can see where it goes and why you would want to be able to do this if you go further in chemistry. So I am saying row 2 plus row 1, so I've got a 0, 1 plus 0 is 1, -1 plus 1 is 0, and -1/2 plus -1/2 is 1. And, oops. Okay, and that is about as good as we can get. We're not going to be able to get rid of, for example, this -1 here, because the only thing that we could do would be to add a multiple of row 3, but then that's going to affect this 0 here. So things would only change. Okay, so it might look like this is not super helpful, but in fact, we can tell quite a lot. So the first thing you'll notice is that we don't have an equation that tells us, so let's just remind ourselves, this would be x1, this is x2, this is x3, and this is x4. We don't have a line which tells us in very simple terms that x4 is equal to some constant. Ideally, we'd have a 1 here and some number here, and then we'd say x4 is equal to that number, but we don't. So this tells us that x4 is what we call a free variable. It can take on any value. So this row over here says x4 is a free variable. It can take any value. So let's start by assigning it any value. So I'm going to say let x4 be t, where t is some element of real numbers. So far, so good. Now, let's think about what this tells us about x3. Well, this equation over here says x3 minus a half x4 is equal to 0. But we know that x4 is equal to some number, although we don't know what that number is. So really what this is saying is that x3 is equal to minus a half t. Similarly, if we have a look at this equation over here, that says x2 plus x4 is equal to 0, but x4 is equal to t. So we've got x2 is equal to minus x4, which is t. Sorry, and I've just seen this should be a plus over here. Okay. And I think I've made a mistake. I think we should have a -1 here. Yeah. So just check somewhere along the line I made a mistake there. So this should be a minus here. So we should have x2 is equal to t. And finally, if we have a look at this line, let's do it in a different color over here. We have x1 minus x3 is equal to 0. So we could rewrite this as x1 is equal to x3, but we know that x3 is equal to a half t, so that's equal to a half t. So putting this all together, and really I'm not expecting you to be able to do this, but I want you to see what this gives us. This says that we have x1 is equal to half t, x2 is equal to t, x3 is equal to half t, and x4 is equal to x4 is equal to t. So this means that we have infinitely many solutions, but we can't just pick random numbers for x1 and x2 and x3 and x4. It says if we pick a value for t, so we pick 2, then for x3 we're going to have 1, for x2 it's going to be equal to, what did I say, we pick 2, I lost track here. Okay, so if t is equal to 2, then we'll have x1 is equal to 1, x2 is equal to 2, x3 is equal to 1, and x4 is equal to 2. If we picked t is equal to 5, then we get different values and so on. So thinking back, what was it that we were trying to do all this time ago? How did we start this all out? Well, we started out by saying we want to find out how much of each chemical we have to have so that everything balances. So this tells us that, for example, if we decide, so remember we have, so what was our final solution? Was x1 is equal to, I'm just trying to remember. Okay, so here are our solutions. Let's try not stepping through all these. So what we were trying to do here was figure out what proportions we need to have of each of our components to make sure that this equation balances. So what our solution is telling us is that if we pick a value for x4, maybe, I don't know, 6 kilograms, from there we know exactly how much CO2 we're going to have, and if we're thinking about when we're creating stuff, we know exactly how much methane and how much oxygen we have to have, because we can work out the corresponding values of x1, x2, and x3. So it's not surprising that we have infinitely many solutions here, because we weren't wanting a specific kind of weight for each of these, but we wanted the proportions, and that's exactly what the solution has given us over here. It's told us that once you pick a t, so you decide, or maybe you decide how much methane you have, so you decide, okay, I know what my X1 is, then you know exactly how much oxygen you need. It's going to be X2, and that tells you how much carbon dioxide and how much water you're going to get. So it gives you the proportions. So there are times when actually what you're wanting is infinitely many solutions, but it's important that it's not any infinitely many random solutions. It's solutions that are linked together in very important proportions. Okay, so that is something that you might have to do in chemistry, but I'm not expecting you to do that in this course. So let's just clarify what you need to know. So from today, what I need you to know is how to take a system of linear equations and transform it into an augmented matrix, and then how to use Gaussian elimination to take that augmented matrix and put it into reduced row echelon form, which, as we've seen, is the thing with ones on the diagonal as much as you can and zeros below the diagonal and wherever you can. And I say, and hence find the solutions to the system, but I really mean if there's a unique solution. So if there's a unique solution. So if we're in a situation like we were here, where you end up with ones on the diagonal, zeros everywhere else, you can read off the unique solution. That I need you to be able to do. I also need you to be able to get a situation like we found over here, where we had no solution. So look and see, oh, I've got a row of all zeros, except on the other side of the equals where I've got a non-zero thing, that's no solution. So you need to be able to identify that. But I don't need you to be able to do what we did in our over here, which is if we've got infinitely many solutions, work out this kind of infinitely many solutions thing here. I just need you to be able to say, oh, we've got infinitely many solutions. I hope that that's clear. Okay, so hence find the solutions to the system. If it's got a unique solution, I need you to be able to say there's no solution because I've got a row of zeros plus some constant. And if I've got a row of all zeros right across both sides of the equal sign, say I've got infinitely many. But you don't need to then go and solve and say x is equal to some function of t, blah, blah, blah. And the other thing, kind of going in the opposite direction, that I need you to do is if I show you a matrix in reduced row echelon form, you need to be able to say, oh, okay, I can see it's got no solutions or one solution or infinitely many. Okay. All right, so we've done quite a lot. And as I say, like most things, like differentiation and integration and all these things, Gauss reduction just takes some practice. So it's called Gauss reduction, Gauss elimination. I've probably used those two terms interchangeably. Yeah, give it a bit of practice. But the key thing to take out of this is the intuition of what the different types of solutions mean. So always have in your mind the unique solution, infinitely many, and no solution. And I personally keep just a 2x2 example here, where a unique solution means I'm really looking at two lines that have a unique intersection. Infinitely many solutions, I'm looking at two lines that are really just lying on top of each other. So that's my infinitely many. And for my no solution, I'm looking at two lines that are parallel, so they never intersect. So those are my kind of those intuitions, because those will help you when you find a solution in a particular situation, understand what it is that you're seeing. Okay, so to practice your intuition, there are three 3x3 systems for you to work with. I will put the full worked solutions in the final version of these notes, but give it a try. All right, see you next week.